So next section is improper integrals. An improper integral is just, well, let's see, I guess I should go to my slide. An improper integral comes in two types. So you might be interested in integrating a function over an unbounded interval. So that would be an interval where at least one of the endpoints is infinite. Or the function could be unbounded. So I might be integrating something like 1 over x, and one of the endpoints would be 0. So the limit as my function approaches 0 is going to be infinite. And so these are going to be the conditions where we can make sense of integrals like that. So we'll start by considering the first type. So I want to integrate a function f of x over either the interval minus infinity b or the interval a to infinity. And if I want to integrate a function over the entire real line, so from minus infinity to infinity, I just think of it as I pick some point in the middle and go up to there and then finish the rest. So the improper integral of f of x over a infinity exists if and only if the limit, so basically all I'm going to do, I want to have an infinity up in the top here. But if I actually plugged in an infinity, most of the time something's going to go wrong. So I want to consider this as a limit. I'll evaluate this integral using a and t, and then take the limit of the resulting function as t goes to infinity. If that limit exists and it's finite, then we say that the improper integral of f of x over a infinity exists. So now it's getting a bit trickier. So our definition of existing means the limit exists and it's finite. And so in particular, that means that if this integral, as I take the limit as t goes to infinity, if I get infinity, then f of x is not integrable over this interval. And then we do exactly the same thing, except now I have t in the bottom. So when I want the lower limit to be able to go to minus infinity, I'm just going to put t in the bottom and take the limit as t goes to minus infinity. And the condition has to be the same. For this to be well defined, I need this limit to exist, and I need it to be a finite value. And so when those limits exist and they're finite, then I'm going to define the improper integral of f of x dx over a infinity to be the value of this limit. So the limit as t goes to infinity, integral from a to t of f of x dx. And then the sort of the complementary piece for the lower limit. So I'm going to define the improper integral from minus infinity to b of f of x dx to be the value of this limit as t goes to minus infinity, the integral of t to b of f of x dx. So you can also add and subtract improper integrals. So all I'm doing here is I'm considering b greater than a. So this is the normal way of setting up an integral. If I think of an interval, I have a lower endpoint of a and an upper endpoint of b. So b has to be greater than a. And so if I integrate f of x from a to infinity, the integral of f of x from b to infinity has to sort of fit inside of that. So what I've done is I've said a to infinity and then b to infinity. And if I do this subtraction, all I want to think about is I'm taking a to infinity, infinity's way over there, and b to infinity, and I'm just sort of chopping off the tail at b. And so probably just as you would expect, what's left is just going to be the integral of f of x from a to b. And then I can do exactly the same thing, but with the other tail. So if I have the integral from minus infinity up to b, so remember b is bigger than a, so this integral, minus infinity up to a of f of x, that's, if you imagine what the area looks like, that's just going to fit in the first area. And so when I do this subtraction, essentially all I'm doing is just chopping off the tail at a. And again, I'm left with the integral from a to b of f of x dx. Okay. And now I want to be able to also make sense of an integral over the entire real line. And so like I mentioned before, the integral from minus infinity to infinity of f of x, this is going to exist if and only if there's a point a such that both the integral from minus infinity up to a and the integral from a to infinity of f of x exist. So in particular, both of those need to be finite. And then if that integral exists, we're just going to define its value. So I'm just splitting up the real line at a point a. So I have numbers bigger than a and numbers smaller than a. The value of this integral is just going to be the sum of these two integrals that we know how to compute already. And so I just wrote down the definitions down below. And the reason we need to be able to split this thing in the middle, why not just define our limit like this? So I take the limit as t goes to infinity of the integral from minus t to t of f of x dx. So that seems like it should work. It's going to get the whole real line. But the problem we run into is I could do something like this. So what I'm doing here is just imagining a line with a slope of 45 degrees. So for positive values of x, that's going to be above the x-axis. And for negative values of x, it's going to be below the x-axis. So if I integrate that from t to t, I'm always going to get 0. But if I split it up anywhere in the middle, I would end up getting a minus infinity and a plus infinity. And kind of like we saw in the first lecture when we were looking at this series of 1, minus 1, plus 1, minus 1, if I have something that I can express as infinity minus infinity, I can't really make any sense out of that. Another good way to imagine what's happening with this is I could also get an integral from minus infinity to infinity by putting a 2t up here. But then that would mean that all of these integrals here, instead of integrating to 0, they would integrate to some, let's see, well, this one would depend on t. But if you're clever about the choice, you can make these all integrate to some non-zero value. And so as you take the limit, then you can get any answer you want to. So if I defined it this way, I would have the limit from minus t to t being 0. But then I'm not going to have the property. So I wanted to be able to do addition and subtraction with my indefinite integrals. And so now if I try to do that, if I want to add two together, I need to be able to break it up somewhere in the middle. And that's going to give me, so if I take a being 0, for instance, I'm going to get minus infinity plus infinity. And that's not defined. On the other hand, if you know for some reason, so for instance, if you know that f of x belongs to a family of functions, so I'm thinking of probability density functions, where this integral does exist, then you're free to evaluate it however you like. So if you know that this integral exists, basically what that's telling you is if you evaluate it correctly and get an answer, that's going to be the correct answer. So you can evaluate it however you like, you'll get the same answer. So you can evaluate it however you like. So this formula, if it was useful, you could use this to evaluate an improper integral. Okay, so now this is probably going to be a little bit strange for some of you. But I want to, for my example, show that for an integer value of alpha that's greater than or equal to 0, this integral, so the integral from 0 to infinity of x to the alpha times e to the minus x squared exists. And so what's going to happen with this particular argument, if I'm pretty sure the way you would actually evaluate this, if you wanted to get a number for an answer, you need to use integration by parts. And when you use integration by parts, you're going to end up with an integral where alpha is 1 smaller. And so if alpha was, say, 10, you would need to use integration by parts 10 times. But I want to get a result that's valid for any alpha that's greater than 0. And so this is kind of a strange situation where, remember, I said this integral exists if the limit is finite. So I can show that the limit is finite without actually finding out what that limit is specifically. But if I can say whatever limit it is, it's less than a finite number, then I can say that this integral exists. This indefinite integral exists. So what I want to show is that if I integrate this function from 0 to t, and then I take the limit as t goes to infinity, I have to get a finite number. And so another sort of shorthand for finite is you just write strictly less than infinity. So that means some real number, some finite real number. So we can recall from the first lecture when I was talking about limits, if p of x is a polynomial and e to the x is the exponential function, then if I take the limit of this as x goes to infinity, I get 0. So in particular, I have this minus x squared here. So if I have e to a negative power, I can also write that as 1 over e to that power. So I can rewrite the integrand here as x to the alpha divided by e to the x squared. And so by using those rules of limits, you can also show that this is going to, the limit of this as x goes to infinity is also going to be 0. And so you might wonder why this plus 2 is up here, because there's no plus 2 in the integrand. And the answer is, I just put it there because I want it there. So it'll pop out later on. And so often when you're trying to work these things out, so I know how to solve this problem already, so I can put the plus 2 there. Otherwise, I wouldn't have put the plus 2 there. I would have done more work. I would have realized, hey, it would be really handy if there was another x squared in this equation. So then I would have gone backwards to this line. I would have added 2 to this exponent. But the point is, it's not meant to be equal to this. It's basically what's going to end up happening is that I can now write this as something times x squared and have my limit here, or my integrand here. And so this, if I consider a sequence as x goes to infinity, this is going to be equal to 0. And so because I know that limit's equal to 0, I can now use the definition to say that there's a value m, so capital M, such that, so this is my integrand again, this value is less than 1 whenever x is greater than m. So this is basically this epsilon delta argument, except for the sequence that's going to infinity. So the epsilon is 1. And then that means because I know the limit exists, there must be some value such that when I'm beyond that value, I'm within epsilon of what I want to be. And so I'm going to choose 1. I can choose any number I want to by the definition of the limit, but I'm going to choose 1 because it's easy to work with. So generally, when you're free to choose a number, if you choose anything other than 0 or 1, you better have a really good reason for it. So now it should be clear why I wanted this x squared here. So if this quantity has to be less than 1, then I can just divide both sides by x squared. And since I'm considering the limit as x goes to infinity, at some point this m is going to be a number bigger than 0. And x, I'm looking at values of x greater than that m. So x is not going to be 0. So I can divide by x as many times as I want to. So I'm going to divide by x twice. So my alpha over 2 becomes an alpha. and my 1 becomes a 1 over x squared. And so the important thing that I've done here is I've taken the integrand and I've bounded it by 1 over x squared. So that means for every value of x greater than m, this thing is going to be less than 1 over x squared. And what that's going to let me do is now if I consider values of t that are greater than m, I'm going to split my integral, so my integral from 0 to t, into a piece from 0 to m and another piece from m up to t. And now what can I say about the first term here? So it's not pretty, but 0 is a constant and m is a constant. So whatever number this is, it's going to be constant. And so t is the only thing that's changing now. This is what I'm taking to be the limit. So I can just rewrite this as a constant. It's no longer really important. If it's constant, it's finite, and all I'm trying to do is show that this thing is not going to be infinite. And also, I've said that this integrand can be bounded by 1 over x squared. So if I were to replace this with 1 over x squared like I've done in the second line, it means it's everywhere for t bigger than m. X squared is bigger than that. So c, this thing, plus the integral from m to t. So remember, one of the properties of the integral was if I had two functions and one of those functions was always bigger than the other function, if I integrate both of those functions over the same integral, then whichever function is always bigger, its integral is also bigger. So that allows me to bound this integral by some constant and the integral of 1 over x squared. And now 1 over x squared, that's something that is actually easy to integrate. So that just becomes minus 1 over x. So 1 over x squared, I can think of that as x to the minus 2 power. And I can use my anti-power rule. And that just means it's going to come from, it's the derivative of minus x to the minus 1. So I get minus x to the minus 1 here, evaluated from m to t. So again, I can rewrite that now as a constant minus this thing here. So this is just to summarize what I've done on the other slide. I now have bounded this integral from 0 to t of this very unhappy looking integrand by this expression over here that's a much simpler expression of t. And so I have c plus 1 over m. So these are just constant. And now remember, what I was trying to do was show that the limit of this guy over here as t goes to infinity is approaching a finite value. And so 1 over t, for t is positive, so this can never be bigger than c plus 1 over m. So I can make an upper bound of c, so that's the integral of my integrand from 0 to m. That's a constant value, so it's going to be finite. And then m is a really big number. And I have 1 over m, so I have to add just a little bit more to my constant. And that gives me an upper bound for no matter what value of t I choose, this is, it's going to be smaller than c plus 1 over m. So that means I can say that the limit as t goes to infinity of the integral from 0 to t of x to the alpha e to the minus x squared, that's going to be less than c plus 1 over m, and that's going to be a finite number, so I write less than infinity. And so without actually evaluating this integral and finding out the number, I was able to show that, that this indefinite integral from 0 to infinity of x to the alpha e to the minus x squared dx, this exists.